Hi and welcome to this higher level applied maths video. Today we're talking about differential equations and specifically we're looking at the integration techniques that will be required for differential equations. So this video itself is just looking at how we integrate. It's not looking at any actual differential equations. Sometimes students end up having to learn differential equations before integration has been fully completed in their maths class. Even if you do have integration fully completed, there are integration techniques that we use in applied maths that you won't meet in maths. This video is going to do a little quick introduction of integration in general for those maybe who need a refresher or maybe you haven't seen integration yet. And then we'll look at the techniques specifically required for the applied maths course. So let's just talk about integration for a while. So if we want to differentiate x to the power of n, and most people will know their rule that you multiply by the power. So you might say something like bring down the power and then reduce the power by 1. So take 1 away from your power. And we end up with n x to the power of n minus 1. And this is a rule that we have in our log tables on page 25. But in general, majority of students will just know how to differentiate this polynomial. So we're talking x to a power. So integration is the opposite of differentiation. So what that means, we're going to undo the differentiation we have above. So that means we're going to start with something. So in this case, x to the power of n, and we're going to do the opposite of the differentiation. So the first thing we're going to do is we're going to add 1 to our power or increase our power by 1, and then we divide by the power. So that gives us x to the power of n plus 1 all over n plus 1. And it's really important that the order we follow it's really important that we follow the correct order, because for differentiation, we multiply by the power, then reduce it. When we go backwards, we are going backwards in both of those steps. So we add 1 to the power first, and then we divide by our power. So that is our integration of polynomials. So you will have to, in your maths course, integrate other types of functions, but this is the most straightforward one that we meet. So let's just kind of go through some basics of integration. So here we have the integral of x squared dx. So this is our symbol to integrate. It's our integral symbol, and it's like a stretched out S. And we also include dx, which tells us what we're integrating with respect to. And these two things come in pairs. So the only time you can integrate is if you have this symbol and you have a d something. So it's usually dx, but it could be dt, it could be d anything. So we're integrating the function x squared with respect to x. What we mean by with respect to is that's the thing we do the rule to. So the x squared here is what we do the rule to. So if we were to kind of think about that, this is the rule we're going to apply. So let's do that actual integration and see what we get. So because integration is the opposite of differentiation, after we differentiate, we might have something that looks like this. dy dx equals x squared. Now, I'm conscious that you may not, I suppose, use this kind of format when you're integrating in maths. It's not required. Most of you probably will have seen it. But what we're going to do is we're going to work backwards with this dy dx. The first thing I'm going to do is I actually bring this dx over to the other side. Okay, so we have dy is equal to x squared dx. Okay, so I separate it into two parts. I get my y's on one side and my x's on the other. And then I apply my integral sign to both sides. So when we're integrating with respect to y, what I have here is a 1 that we don't write. So the integral of our dy is simply y. Okay, so our integral of dy is simply y. And then on the right-hand side, we're integrating with respect to x. So using our rule of add 1 to our power and then divide by our power. So more often in maths, they will give you the integral like this, and they might have a y there. Okay, so you won't necessarily have to integrate the left-hand side. For us in applied maths, it's important that we understand where we're able to break that dy dx up, or whatever the equivalent is, and integrate both sides, because that is the basis for our differential equations. And you'll be able to see that when you move into differential equations and when you're revising those. So we've integrated now and we found our y. So we integrated x squared dx and we got x cubed over 3. However, if we think about integration as the opposite of differentiation, we could have had an original equation like this. Because if I had x cubed over 3 plus 2, I would have differentiated. So dy dx equals, I would have brought down my power, taken 1 away from my power, and then the 2 would have disappeared. So that would have given me dy dx equals x squared. So we run into a little bit of a problem with integration. And that is because constants, when we differentiate them, disappear. They go to 0. So remember, differentiation is slope. The slope of a constant is 0, because that plus 2 effectively disappears. We could have had a constant that disappears and we don't know about it. And that's something you need to really take on board when we're doing any integration. So how we get around this is we use a plus c, meaning plus some constant. Now that constant could have been anything. It could have been a 0. And this plus c generalizes the integration. Okay, so it makes it correct, because we're accounting for the fact there could be a c. And we will see in the future how it is possible for us to figure out the value for that c, and how sometimes we don't need to put that in at all. So on page 26, we have all the rules for integration. So in maths, we generally only use this we're only going to be using that first box. For applied maths, we use the whole page. But what I want to draw your attention to is the little bit of information up here, and that is that the constant of integration is omitted. So basically what that means is you need to put in a plus c for any of these. So there's a plus c that should be beside each of these answers, and they have omitted them, and it is up to you to put them in. So bear that in mind. So again, we will look at when we don't need to put in the plus c and how we can work out what that c is as well. So before we go into any kind of examples of our integration, I want to talk a little bit about differentiation, because they go hand in hand, and some of our integration techniques actually use differentiation. So make sure you're 100% happy with differentiation before you move forward. So I've linked the videos from the maths course on differentiation and integration in the description below if you want to go back over them. But here we're going to focus on the chain rule. Again, you may have done this in a bit of depth in your maths course, or you may not. So because we go so much deeper with our integration in applied maths, understanding the chain rule and what it's doing can make a big difference to our work. So we're going to look at some composite functions. So you would have studied composite functions in the function section. And composite function means that we're putting functions into other functions. So I've given you 3 functions here. F of x is sine x, g of x is x squared, and h of x is 7x plus 1. So we're going to get f after g of x, which means f after you put in g of x, which is putting in an x squared, and that means we get sine x squared. So then we do g after f of x, which is g of sine x, and that is putting sine x in a bracket to be squared. Now, notation for squaring, sine, cos, or tan, moves that squared onto the word itself. So that's written as sine squared x. The part 1 and part 2, those two cannot be mixed up. In the first one, it is the x that's squared. In the second one, it's the whole thing. And then our last one has 3 functions pulled together. So we have f after g of h of x. So then we have f after, so we have g of 7x plus 1, so that's going to be squared. And then we plug that into f, so we get sine of 7x plus 1 all to be squared. And if you want to kind of do a bit more with that, you can absolutely square that out. Really all we want to do here is, so that squared, is get to grips with our composite functions. So that's our answer for part 3 if you want to expand that bracket squared. So why are we talking about composite functions? Well, the reason we have the chain rule is for composite functions. So hopefully when you did that in maths, you made that connection. If you didn't, now we're really going to focus on that connection. So when you learn the chain rule, you probably got introduced to it with the formula. You may not continue to use the formula. The formula is quite cumbersome. If you do use the formula, then generally you do talk about composite functions. It's hard to avoid it. What I would find is students tend to be able to get away with a little bit less in the maths course, and it really depends on where you learn differentiation. So if you're learning differentiation quite early on in 5th year after functions, this can be quite overwhelming, and just understanding the rule of chain rule is enough. If you're kind of in 6th year or later in 6th year when you learn it, then you can go a little bit deeper with it. So let's take an example of a function that if we were to differentiate it needs the chain rule. So here we have a bracket to a power. So that's really easy to identify as needing the chain rule. So basically, in short, the chain rule is differentiate the function as per the rule in the log tables. Okay, so that means the whole thing. So what we have here is 3x to the power of 4 minus 5x to the power of 3. Differentiating that means bring down our power, then take one away from our power. Okay, then we're going to multiply that by the derivative of the inner function. So we're going to multiply that by what's inside the bracket, and we're going to make sure that that's differentiated. So let's do the first part. Let's say dy dx equals, bring down our power, that's 3, bracket 3x to the power of 4 minus 5x, and then take one away from your power. Then we're going to multiply that by the derivative of the inner function. So our inner function here is 3x to the power of 4 minus 5x. Again, 3x power of 4, bring down your power, take one away from your power. Same for minus 5x. That gives us 12x cubed minus 5. Bringing that together gives us dy dx. I've multiplied my 3 by my 12x cubed minus 5. And then multiplied it by my bracket squared. I'm not doing any expansion or anything like that. So most students will be able to apply that chain rule in that way, but we want to go a little bit deeper and understand, well, what exactly is happening here. So in order to work backwards and to work backwards properly, we need to have a very good understanding of it. So here are some examples that require the chain rule, and what I want you to start thinking about is how these are all examples of composite functions. So our first one here is y equals 2x squared plus 3x all to the power of 5. So we have an outer function, which we'll call x to the power of 5. We have an inner function, which is 2x squared plus 3x. And this y is basically f after g of x. So what we're doing is we're differentiating the f of x. So you're bringing down your power and taking one away from your power, but you're leaving what's inside. And then you multiply by the derivative of the inner function. So you're differentiating g of x, which gives us 4x plus 3. I'm not even going to tidy that up because really all I want in the focus of this is understanding, can you spot the two functions that are coming together to make our lovely composite function, and can you then see how the chain rule is working? So then we have something a little bit trickier maybe to identify as the chain rule, and that is cos 5x. So if you've learned to differentiate your trigonometric functions, you'll know that they need a slightly different rule than we see in the log tables in some cases. And the reason we need that is because they're composite functions. So we have an outer function, which will be cos x. We have an inner function, which is 5x. And now we have our composite function. So if we were to differentiate that, we have dy dx equals. So the first thing we need to do is we need to differentiate our cos x. That's our f of x, and that goes to minus sine, and we leave the 5x in there as it is. And then you multiply it by the derivative of the inner function, which is our g of x. So we're multiplying that by 5. So you would have probably very quickly learned about multiplying by that coefficient. It's not the coefficient, it is the derivative of 5x. Now, for a linear like 5x, that's going to be the same, but just to be very clear on what we're doing. I keep saying it, but the technicality we need in applied maths is so much more than you'll ever need in maths. So if you think, oh, but my integration is great in maths, it's going to be great in applied maths, there's so much extra that we need. So don't take that for granted. So here's our last one. We have x equals sine x, and then our inner function is 2x plus 3. That gives us the derivative function f after g of x. Differentiating that, we're going to differentiate our sine. That goes to cos 2x plus 3, multiplied by the derivative of the inner function, which is going to give us 2. That 2 needs to sit in front, so 2 cos 2x plus 3. So what we want to look at is using this idea to work backwards. So when we're integrating, so if we had something, if we had something that the chain rule was used to get the derivative of, when we're working backwards, can we basically use the chain rule in reverse? So here's page 26. These are our rules for integration. So like I said, the whole page is going to be used. And our focus now is to try and understand, can we apply some of our basic rules, and can we apply some basic chain rules in reverse? So I'm going to take, when I say a basic chain rule in reverse, what I mean is one that we can do just going backwards. We are going to have another more stringent technique that can be used for harder examples. So we're going to use cos 3x dx, which is one that if you've done integration in maths, you should be absolutely fine to integrate. But let's really take a look at what we have. So remember that if we want to differentiate with the chain rule, we differentiate the function as per the rule in the log tables, and then we multiply by the derivative of the inner function. So to integrate, it's the opposite. We're going to integrate the function as per the rule, and then we're going to divide by the derivative of the inner function. When we looked at the integration at the start of the video, the order there was really important because we had a division and a subtraction. So here, because it's a multiplication and division, the order here is not as important. We're not going to panic. If you divide by the derivative first and then integrate, you're going to get the same answer. So for cos 3x dx, we're going to integrate the function as per the rule in the log tables. So on page 26, they tell us that the integral of cos x is sine x. So in order to do that, we're going to say that that's sine 3x. And we're going to divide that by the derivative of the inner function, which would have been our 3x. So we're going to divide by 3. And that gives us the answer y equals sine 3x over 3 plus c. So that is the chain rule in reverse. One key idea that you may have already started to pick up is that differentiation is all about multiplication, while integration is all about division. And that makes sense since they're the opposites of each other. So that is an integration that we can apply very quickly that is using the chain rule in reverse. So here are the rules on page 26 for integration. So later on in the video, I'm going to introduce you to a process that properly deals with the chain rule. So it's a longer process, and it's one that, if we can avoid, we want to be able to avoid. So we're going to focus on these basic cases. And what I mean by basic cases, they're absolutely fine to work using the idea of the backwards chain rule. So there's very few that we really need to do in this case, and that is 1 over x, cos x, and sin x. So these three functions here. And generally speaking, these are the ones that you will have already met in maths if you've worked with integration. So these are ones where we could have already seen the backwards chain rule in action without too much upset. So let's start by working on some kind of straightforward indefinite integrals. So indefinite means we're going to have a plus c. We don't know for sure what the answer is, so make sure we don't forget the constant of integration every time we do our integral. So first one is add 1 to your power, divide by your power. Add 1 to your power, divide by your power, plus c. So lovely straightforward polynomial. Our next one here is an exponential. So on page 26 of your log tables, we have the fourth rule down, which tells us e to the power of ax. So it tells us e to the power of ax is going to become 1 over a e to the power of ax. This is actually a simple case of going backwards with the chain rule, but just like for differentiation, they actually give us it as a single line on the differentiation page, and in this case the integration page, which makes it much easier to work with. So we get 1 over, it looks like the coefficient, but it's actually the derivative. So it's 1 over 2 a e to the power of 2x plus c. Remember, e to the power of anything never changes when it when it's differentiated, and it will never change when it's integrated. So our next one is sine 5x. Notice how this is a composite function. There is a 5x instead of just an x. One way to identify that is in the log tables, we have sine x, and that tells us it goes to minus cos x, but we don't have any number in front, okay? Because what we have here is more complicated than here, that's generally a good indication that we're going to be using the chain rule. So here we have minus cos 5x. We're going to divide it by 5, and then we have a plus c. This last one might look a little bit tricky, but all we're going to do to make it easier is we're going to put a 1 in front and move the dx out to the side. So that dx written on top just makes it a little bit easier to write, but it can confuse us as we're starting integration. By the time you're deeper into this, that won't throw you anymore. Once we've separated this out, this is a type of integral that you will not have met in your maths class. So you will only see this in applied maths. So if you take a look at page 26, you're looking for a formula, an f of x, the left-hand side of any of the boxes that mirrors this. And if you look at the second box, the last one down, we have 1 over x squared plus a squared, and that gives us 1 over a tan inverse x over a. So that gives us 1 over, the a is 3 because that's where our 9 came from. So there's our a squared. This one's 9, so it's 3 squared. Then we have tan inverse x over 3. Don't forget your plus c. So in this example, I have one that's probably the hardest to identify as needing the chain rule. You might search for a formula on page 26, something that looks like that. But what you'll notice is even though we have about 6 there that have 1 over and then x's on the bottom and numbers, they all have an x squared. None of them have just x. So this is not a rule that maybe you can spot straight off. This is actually a version of 1 over x going to the natural log of the absolute value of x. And it is a chain rule. So just really to really spot this, we have a 2x plus 1 gone in there instead of just an x. So what we need to do to integrate this is we're going to integrate this as normal. So that is ln, whatever's on the bottom, so that's 2x plus 1, has to be in my absolute value signs because the ln can only be of a positive number. So remember, ln, natural log, is base e. E is a positive number, so that means it can only give us we can only get the log of a positive number. It's not possible to ever put a power on e and make it negative. So think about using the chain rule. We have integrated as normal, and now we divide by the derivative of the inner function. So that's a 2 plus c. Often what we see happen in this case is we write it rather than over 2 as a half. Now, the reason we tend to do it like this is because we can then use our law of logs and bring that half to be a power. So you could have this as ln 2x plus 1, and that's all to the power of a half here, plus c. So that's one of our rules of logs, and that can even go a step further and be ln square root of 2x plus 1. Those absolute value signs mean that if x were like some big negative number, that we still have a positive number in that square root, and we have plus c. So now we're going to look at definite integrals. So the question is, well, what's the difference? There's absolutely no difference in how we integrate, but what is going to be different is the fact that indefinite integrals, they finish with their plus c. The definite integrals are going to give us a number answer. So they actually calculate the area under a curve. And because of the way they're calculated, we don't need to put the plus c in, because if you put a plus c in both parts, it ends up cancelling each other out during the calculation, or basically c minus c. That's what we'll end up with. So you are welcome to put it in, but you're not going to get any benefit from it. So just be careful as you move into your definite integrals to not get out of the habit of the plus c when we're dealing with indefinite integrals. The way that indefinite and definite integrals look is slightly different. So when we see a definite integral, we're going to have what are called limits of integration, and there's going to be two. We're going to have an upper limit and a lower limit. And this is what it'll look like. We have our upper limit and our lower limit, and these are the values that we are going to plug in after we have integrated our function. So how do they actually work? So let's take the example that was just on the previous slide, and we have x squared dx. We're integrating that between 3 and 6. So our first step is to integrate as normal. So this is a polynomial. We're adding 1 to our power and then dividing by our power. So this time I don't need to add a plus c. Instead, what I'm going to do is I'm going to bring down my limits of integration, which are 6 and 3. What that means is we first sub in the higher value, which in this case is 6. So we have 6 to the power of 3 plus 3. Then we take away the substitution of the smaller power. So it's going to look like this. So just a bit of color coding so you can follow it. So there's our 3. Our 6, and then there's our 3 being plugged in. So at this point, you'll be able to see, like, if I have my plus c here, I'd have a plus c and a minus, or and a plus c that would effectively be subtracted. So I want to make sure that I don't do any more work than I need to. So the plus c can be ignored in that case. So you can evaluate that very quickly in your calculator, but I'm going to do it just step by step, just for the purpose of our first example of it. So we get 72, take away 9, and that leaves us with 63. So if you put that line here straight into your calculator, you would have been able to get that. So our answer is a number. It's not going to give us a function, and we do not require the use of a plus c in this case. So let's look at example 3. It's another definite integral question. So first thing we're going to do is we're going to integrate. So that's 6x squared divided by 2. We can divide that in and tidy that up a bit, which gives us 3x squared. And we want to evaluate that between 3 and 1. So that gives me 3 squared minus 3, 1 squared. And that gives us 27, take away 3, which is 24. So lovely and quick, and just be careful with your substitution. So example 4, so we're still using page 26 for our log tables for any functions that maybe we don't know. the integral of off the top of our head, so anything that's not a polynomial. So we're integrating e to the power of x. Now e to the power of x actually doesn't change, so it's going to stay e to the power of x. We're going to evaluate that between ln 3 and 0. So we get e to the power of ln 3 minus e to the power of 0. E, ln undo each other. So that's just going to leave us at 3, and that's take away 1, and that gives us 2. So just to kind of go through that with just a little bit more depth for anyone who needs it, that's e to the power of log to base e3. And if you go to your log tables and we look at the page for our indices and logs, page 21, we have a little formula. It's the third one down on the very right column, and it says a log to base ax equals just x. So effectively, a log to base a undo each other, the same way that e log to base e undo each other. So that's e ln effectively undo each other and leave us simply with the number that was there. So in that case, 3. So that's a nice quick one. Logs and indices, well, natural logs in particular, are going to be very important when we're doing integration in applied maths. So it's worth making sure your logs and your rules of logs and your understanding of logs are, up to scratch. So I've linked the logs video in the description below. Don't worry too much about exponential functions. Just focus on your rules of logs and changing logs to exponentials. Now, this might be one that you're not familiar with, so make sure you page 26 of your log tables open. So we want to integrate between 3 over 2 and 3. It's 1 over the square root of 9 minus x squared, and that dx can be written to the side, which makes it a little bit easier to see. And in the second box on page 26, third one down, we have this function here. And they tell us when that's integrated, it becomes sine inverse x over a. And that matches what we have here, a being 3. So we have sine inverse x, which is simply x over 3. So this is going to be evaluated between 3 and 3 over 2. So we're going to do sine inverse of 3 over 3 minus sine inverse 3 over 2 divided by 3, which is basically the sine inverse of 1 minus the sine inverse of a half. Okay. So if you haven't worked with your trigonometric functions in maths yet, it's really important to note that when we're in integration and we're using any trigonometric functions, you have to work in radians. Okay, so we have to work in radians. So in this case, if you're going to your calculator, make sure your calculator is in radians. I would suggest using page 13 instead. It's a lot more efficient. It's a lot easier to work with. The conversion between degrees and radians, it helps you make better sense of it. And I'm using page 13 and I can see that the sine of pi over 2 is 1. So sine inverse of 1 is pi over 2 minus, and then sine of 30 degrees or pi over 6 is a half. So then that's pi over 6. You can use your calculator to subtract them relatively quickly, but you're getting 3 pi over 6 minus pi over 6, which is 2 pi over 6, which is pi over 3, which is actually 60 degrees for anyone who is interested. Now, the logic behind having to use radians is one that, again, hopefully you've seen in maths, but I'll just run through it very quickly for anybody who may not be familiar with the logic and the reasoning behind that. Okay, so why do we always use radians in calculus? So there's really two main reasons. So the first thing I'd say is really make an effort to understand what radians are. You don't use a huge amount of radians, so it can be helpful to think in terms of degrees and its corresponding radians. Page 13 in your log tables is a huge help for that. And I think most students doing any kind of calculations in trigonometry or using trigonometric functions in calculus, in maths or applied maths, page 13 is going to be a huge help to you. So 1 radian is the angle where the arc length is equal to the length of the radius. So here we can see in the diagram they're all or. So what that means in terms of like linking degrees to radians is 360 degrees is 2 pi radians. And we think of that from our circumference formula, which is 2 pi times the radius gets us the circumference. So 360 degrees gives us 2 pi radians. So what radians do, they basically relate a linear measure to an angle measure. Now, radians are one that we'll meet in a few different places in applied maths, and one of the main places where we meet our radians is in circular motion. So if you haven't done circular motion yet, you will meet that angular velocity is in radians per second. But one thing to note about that is actually radians themselves, because what we have, and if you think about this, because what we have is the arc length, okay, divided by the radius. And if you measure them both, just say in centimeters, effectively your radian calculation has no unit. So when we get to looking at dimensional analysis, radian isn't a true unit. It's a word that we use to describe the ratio of length to the length of the arc to the radius, but it isn't actually a unit that we have like meters or for meters cubed or meters per second. It's not a true unit. So I suppose getting back on track, well, why are we always using it in calculus? So if you plot the graph, you have a better sense of what's going on. So if we plot the graph so that the x and y axis have the same scale, this is what we see for the sine graph, and it's nothing. You can't see anything at all. And if you've done your trigonometric functions, you will be looking at this thinking, that's not what it's meant to look like. So the problem is the scale is way off. So here we're using the same scale. So a box is 20 on the x-axis and it's 20 on the y-axis. So if we change this into radians, this is what we get. So it's much better for us when we're plotting it to have the x and y axis on the same scale. So we want to see really our units being used as radians rather than degrees. But that doesn't really explain why we have it in calculus. It's just a nice way to kind of visually remember that actually, yeah, it's not great for a graph. So the other way to, well, the real important piece for us from a calculus point of view is the rules for differentiating and integrating are specifically designed for radians. So go back to your integration or your differentiation from first principles, and that is how we differentiate. And when they decided to differentiate sine and cos and so on, we were looking specifically at the angle being in radians. Okay, so in terms of limits, we're basically saying, well, the limit as x goes to 0 of sine x over x is 1, but that is only true if x is in radians. So in order for us to use integration or differentiation and the degrees and the unit of measure for the angle is degrees, we would actually have to use the chain rule, okay? Because it would be a function within a function, it would be a composite function. So that's really the bit. It's slightly kind of probably not as easy to remember, which is why I like to kind of throw the graph in there. But it'll give you a better sense of it's not just a nice to have, it is you must. There is no option. You must use radians in any calculus that you do. So here's another trigonometric function. We've sine squared x. X is obviously the angle, and we can see that the angle is evaluated between 0 and pi over 4. That is 0 radians and pi over 4 radians, equivalent to 0 degrees and 45 degrees. So that's a little bit easier to spot, easier to remember, because we can see that pi there to kind of remind us that it's radians. So the first thing we need to do is we need to integrate this. And if you take a look at page 26, we have a formula that helps us integrate sine squared x, and it is a half x minus a half sine 2x. So that is going to give us 1/2 x minus a half sine 2x, exactly as it is. And then we're going to evaluate this all between pi over 4 and 0. So that gives us a half. I'm going to leave that outside the whole thing. We're going to evaluate pi over 4 minus a half sine 2 pi over 4 minus, so that gives us 0, minus a half sine 2 times 0. So 2 times 0 is 0. The sign of 0, if you want to check it, is 0. So that whole second bracket is worth nothing. So that gives us a half pi over 4 minus a half. That is actually sine pi over 2. Again, I will be suggesting you're using page 13 rather than your calculator to evaluate these, because it's much quicker and you're not messing around changing your calculator into radians or anything like that. So we have a half times pi over 4 minus a half. This goes to 1, and that gives us half pi over 4 minus a half, and that gives us final answer pi over 8 minus a quarter. So now that we've covered the basics of integration, pretty much what you'll have covered in your maths class, and we've added in a few extra formulas from page 26, but all in all, they are the same basic techniques. Now is the first new technique we're going to learn for applied maths. It's called integration by parts. So integration by parts is a technique used to integrate the product of two functions. So remember, integration is the opposite of differentiation. And this integration by parts is actually the opposite of the product rule. So the formula itself is derived from the product rule for differentiation, and it's rearranged into a form suitable for integration. So it looks like this. It's in our log tables on page 26 at the very bottom, and it's the integral of u dv is equal to u times v minus the integral of v du. So where we break our original integral into u, which is the function we differentiate, and dv, the function we will integrate. So when you use, it's going to be useful when you have a product of two functions where direct integration is going to be difficult. So the formula, like I said, is found on page 26, and the steps are identify and choose the parts of the product as u and dv. So this must be in a very specific order, and we can call this order in late. You can pronounce that in late, in latte, whatever way you want to pronounce it, as long as you remember it. I'm going to go through it in a little bit more detail in the next slide. We're going to differentiate u to get du and integrate dv to get v. We're going to apply the formula, and then we're going to simplify and solve the remaining integral. We may run into questions where we have to do integration by parts twice in order to get an answer out. So here is the formula for integration by parts, and the order in which we want to break up our function into u and dv follows very specific rules. So this is the inlate rule for integration by parts. So when using integration by parts, we must carefully choose which part of the integrand becomes u to differentiate and which becomes dv to integrate. So to apply the integration by parts rule effectively, the function must be chosen in a specific order given by this rule. So IN stands for inverse. They are inverse functions. L for logarithms, A for algebra, T for trigonometric, and E for exponential. So when we see a question and we know we're working integration by parts, we'll write IN-LATE on our page, and we will make sure that before we break it into our u and our dv, we have each of the products, so each of the pieces of the product, written in this order. So just a little note on this. If both parts are the same, and where we probably see this the most is algebra. So if there are two algebra parts, then although integration by parts will generally work, it is definitely not the easiest way to work, and we have a more suitable type of integration. So what I would say to you is make sure that when you see a question that you will generally, for us in applied maths, have two different types. So you'll have like an inverse and a logarithm, or a logarithm and an algebra piece, and a trigonometric piece and exponential. You should have two different pieces. If you don't, consider other types of integration first. So example 7, it's going to be integration by parts. We can identify that as integration by parts because we have two things multiplied together. So we have x and then e to the power of x. So this is our formula. To make sure that we apply the formula correctly, we need to think about our INLATE. That is the order. So the two things that we have an algebraic piece and we have an exponential, and they are in the correct order. So then what we have here is the integral of u dv. This is our dv part, and that is our u. So we set that up as u equals x, so du dx equals 1. And what we want to do here is we want to separate the u's on one side and the x's on the other. Then we have the next part, which is dv, and that's going to equal e to the power of x dx. We're going to integrate both sides. That gives us v equals the integral of e to the power of x is simply e to the power of x. Now, this is an indefinite integral. There's no limits of integration on the full question, so we could put a plus c in here, but that's going to complicate things. So what we're going to do is we're going to wait until the very end and add our plus c into the whole thing. So there's no need to put the plus c in there just yet. So what we're going to do is to find the integral of x e to the power of x dx. We're going to follow this formula above. So the formula here is u, which is x, times v e to the power of x, minus the integral of v e to the power of x du, which is dx. And that's going to give me x e to the power of x minus integrating e to the power of x leaves us e to the power of x. And then, because we're at the end, we're going to add our plus c. So example 8, we have another integration by parts. We can recognize that by the fact that we have a product here, so x times ln x. We have our formula here, but we need to make sure that each part of the product is in the correct order. So we have two parts. We have an algebraic part, and we also have a log part. Now, unfortunately, they're in the wrong order, so we need to flip them. So this is a definite integral, so we have our limits of integration there, and we're going to flip this into ln x times x dx. So they're not kind of flipping it to confuse you or anything like that. That would be the convention we would write it, but we need to flip it in order to have it in the correct order for integration by parts. So we are integrating, and we are integrating u dv, which means that this part is our u and this part is our dv. So we have u equals ln x, and we want to differentiate that. So du dx, page 25, the natural log, differentiates to 1 over x. So du equals 1 over x dx. Then we have dv equals x dx, and we're going to integrate both sides there. So that's v equals x squared over 2. So there'd be no need for a plus c anywhere in this question. So now we're looking to find the answer of x ln x dx. So we're going to sub in our u, which is ln x, times v, which is x squared over 2, minus the integral of v, which is x squared over 2, times du. So that's 1 over x dx. So we can do a little bit of tidy up here. So the x at the bottom and an x on the top divide into each other. So that leaves us with x over 2. So the next line is ln x squared over 2, minus, so we're integrating this, so we add 1 to the power. and then divide by the power. So we're dividing by 2, but there's already a 2 there, so we're actually dividing by 4. And we're going to evaluate this between e and 1. So that is ln e squared over 2 minus e squared over 4 minus ln 1 squared over 2 minus 1 squared over 4. So ln e is 1, so that leaves us with e squared over 2 minus e squared over 4, which can be brought together. ln 1 is 0, so that gives us minus a quarter. So just to finish that off, e squared over 2 minus e squared over 4 is going to equal the same as 2e squared over 4 minus e squared over 4, which we can then simplify to just e squared over 4. And then we're taking away a minus quarter, so that's plus a quarter. And that is our final answer. It is in terms of e, and if you want to get it as a decimal, if they asked, we want to put that into the calculator and you can convert. So this is our last integration by parts. You can identify it as integration by parts because we have that multiplication. E to the power of x times sine x. So we're using this formula. We want to make sure that we're in the right order. We have two pieces. We have a trigonometric piece and we have an exponential piece. Okay, so anytime we have a trigonometric function within an integration by parts, something strange is going to happen. Let's start this as per normal, and when we get to that part, I'll explain a little bit more. So the first thing we need to make sure is that we're in the right order. We aren't, so we're going to change this to the sine of x times e to the power of x dx, and that is going to be my u, and this is going to be my dv. So u is sine x, du dx. When we differentiate this, we get cos x, and du gives me cos x dx. My dv is equal to e to the power of x dx. So we're integrating both sides. V equals e to the power of x. So when we're working out our answer, we have the integral of e to the power of x sine x dx equals u, which is sine x, times v, which is e to the power of x, minus the integral of v, e to the power of x, du, which is cos x dx. Now, here's where we run into a little bit of a problem. We end up having to do integration by parts again, because this part here, this integral, requires integration by parts because again it is a multiplication. It has our 2 bits, then they are exponential and trigonometric, just like our original piece. So the reason we get that is because sine turns into cos, and cos then will turn back into sine. So effectively you end up with kind of a circular issue. So I'm going to change my color slightly. So we're going to work on e to the power of x cos x dx. The first thing I'm going to do is notice that that's in the wrong order. So I'm going to change that to be cos x, the trigonometric piece first. And then we have e to the power of x dx. So this is my u and this is my dv. Now, I'm going to cheat a little bit because my dv is the exact same as over here, okay? So that's not going to change. I'm going to work in the different color over here. So I do know my u is cos x. This is for the second go. So du dx is minus sine x. So what's your signs there? And then du is minus sine x dx. So then if we were to plug this into the integration by parts formula, we have u times v, which I'm using from here because it's exactly the same, minus the integral of v e to the power of x du, which in this case is minus sine x dx. Okay, so if I tidy that up a little bit, I get e to the power of x cos x, and I have two minuses, so that actually makes a plus e to the power of x sine x dx. And this, again, needs integration by parts. So what will happen is you will keep going forever and you will keep getting integration by parts. There's no end to this. So we need to have a little bit of a trick. So we're going to take the two things we've done already and we're going to bring them together. So this piece here, we have integrated. I'm going to bring that back into my original and show you the trick that we do to get our final answer. So just to give ourselves a bit more space, I'm going back to my first line here, and I'm just going to plug in the bit that we've done in black. So we have the integral of e to the power of x sine x dx. That's the thing we want. And we know that's equal to e to the power of x sine x minus, instead of that, e to the power of x cos x dx integral, I'm going to plug in what we've just worked out, which is e to the power of x cos x plus the integral of e to the power of x sine x dx. And we're not going to try and integrate this piece again, this piece here, because if you notice, it's actually the exact same as what we want to begin with. So we can use that fact. Now, to make life a little bit easier, we're going to let that whole thing that we want equal something that's a bit easier to manage. So I'm going to call that just capital A. You can use any letter or you can leave it as is. So what we effectively have here is A equals e to the power of x sine x minus e to the power of x cos x minus A. I'm going to bring my a's together and I get, well, 2a's equal e to the power of x sine x minus e to the power of x cos x. And I want an answer for A, so I'm going to divide that across by 2. So e to the power of x sine x minus e to the power of x cos x all over 2. And if you want to write that in kind of a slightly nicer way, we can pull out that e to the power of x and the 2 in front, and we can do sine x minus cos x, and that's our answer. So the little trick is to do your integration by parts the second time, but stop, plug it back in and notice what you have in this new integral matches what you want, what the original question asked you for, and we can use that fact. It's worth practicing a few of these because it's a little bit tricky and it's a little bit different. If you were caught in an exam, this may not be something you would even think about. So that little trick, it is important and it will come with practice. And I nearly forgot, and I'm sure you're all shouting at the screen, we have an indefinite integral. So to make sure our answer is fully correct, we need to make sure that we put our plus c at the end. You can see how easy it is to forget that plus c when there's so much else going on. So just be really mindful. It can be helpful at the start of a question when you know it's an indefinite integral to kind of highlight that. Chances are when we're working with our differential equations, we generally don't have a plus c. There will be values that we will be plugging in. So we're going to move on to our last type of integration. And before we look at that, again, I want to go back to the chain rule. Now, we've already looked at the chain rule at the start of this video, so I'm going to go through it quite quickly. So here are some examples of the chain rule, and I said to really think about them in terms of the composite function. So our f of x at g of x and how this was then f after g of x. Same here, f of x, g of x, and how this was f after g of x. F of x, g of x, and f after g of x. So we're going to use that idea and we're going to go a little bit deeper into it, and we're going to really focus on the formula of the chain rule and then how we can use that for integration. So not just basic examples like we had at the start of the video. So use substitution for integration. So this is obviously often called just integration by substitution. You might find more resources on it if you use the idea of use substitution. But basically integration by substitution, which is also known as use substitution, is a technique used to simplify integrals by substituting a variable within the integral. So we simplify it using substitution, hence the name. The technique is particularly useful when dealing with complex integrals, and it's particularly useful when dealing with composite functions or where the integrand contains a function and its derivative. So I suppose our focus is on composite functions, and I want to focus on the idea of that chain rule in a bit more depth, which will hopefully help you to understand this integration by substitution or use substitution a little bit better. So let's explore using the chain rule formula from the log tables. So here's an example: y equals 2x squared plus 3x to the power of 5. So the formula in our log table is f of x is equal to u after v of x. So we're going to define two parts. We have a v and we have a u. So v is our inner function. So we can see we have v is our inner function, which is going to match here. So our v is going to be 2x squared plus 3x. Now, our u has to be defined in terms of v. So what that means is the whole function, so think of u as the full thing, is going to be v to the power of 5. So rather than writing 2x squared plus 3x all to the power of 5, we're defining u in terms of v. And the reason for that is if you look at the formula for the derivative, we have du dv, which asks us to differentiate u with respect to v. So we're going to have u is equal to v to the power of 5. So du dv is equal to 5v to the power of 4. Our v is 2x squared plus 3x. This formula tells us to find dv dx, so differentiate v with respect to x, and that gives me 4x plus 3. And then the final answer for the derivative is going to be du dv, which is 5v to the power of 4, times dv dx, which is 4x plus 3. And then we're subbing in for our v. So that is 2x squared plus 3x, and then 4x plus 3. So because we can do this a lot quicker, we tend to either not use the formula at all or move away from it as we become more familiar with it. However, the idea of using this formula is going to really help us as we try and move backwards because we use the same idea. Okay, so our steps for integration by substitution are: choose your u, so select u as the part of the expression that will simplify the integral. Differentiate u, so find du in terms of dx. Substitute, so replace the original variable and expression in the integral with u and du. Integrate, so now that we've something that's much simpler, we're going to perform that integration. And then back substitute, so after integration you go back and replace u with what you had originally. So one thing to note is you always want to sub back in before calculating your answer using the limits of integration. So when we have a definite integral, you always sub back in first. So let's use these steps and let's see if we can figure out how we integrate using use substitution. So let's try some integration using use substitution. Here we have the integral of 2x plus 3 to the power of 5 dx. This is a lovely straightforward little example, and we could probably do this using the skills we learned at the start of the video, just thinking about it logically. However, we're going to try and use this new technique, which is integration by substitution or use substitution. So it's called use substitution because we generally use the letter u to stand in to make the integral simpler. So we generally want to try and recognize that we have a composite function of some sort and that there is an inner function. So the inner function is going to be the one that we want to label as u. So in this example, it's going to be the 2x plus 3. So we're going to take that and define that as our u. which is 2x plus 3. So what we want to do with our integral is we want to then simplify it by replacing that inner function with just the letter u. However, because I've replaced the x with the u, I also want to replace the dx. So how I do that is I differentiate the u that I've chosen, so du dx, and that's going to give us 2. And then I separate out the u's on one side and the x's on the other. And specifically what I want to do is get dx on its own because I have a dx here that I want to replace in some way with a u. So I'm going to bring this 2 over the equals as well. So that gives me a half du equals dx. So instead of my dx, I'm going to plug in a half du. So what that ends up giving us is u to the power of 5 over 2 du. And now I'm going to integrate as normal. Add 1 to my power, divide by my power. So in this case, I'm dividing by 6. There's already a 2 here, so that's 12. And I'm also going to have a plus c because we have an indefinite integral. So now, before I finish, I have to go back and plug back in my u because we added in the u, so we need to make sure we take that out. So that means we're going to have 2x plus 3 to the power of 6 all over 12 plus c, my constant of integration. So example 10, integration by substitution. The first thing you want to do is, can we identify that it's substitution? Now, at first glance, you might say, is this not integration by parts because we have multiplication? That is absolutely true. However, what we want to identify first is, do we have a composite function? And we do. And we can see the composite function piece right here. So it should be e to the power of x, but we've e to the power of tan x. So we have that in our function. And if you can identify that in our function, that means you can identify your u. Remember, your u is always the inner function when we talk about it in terms of a composite function. It won't always be that easy to identify it, but if you can identify it, it's a great way to start your question. So because we want to replace x with u, we also want to replace the dx. And we do that by differentiating our u. Now, our differentiation rules are on page 25, and tan x might be one that you may not have seen or seen a lot of, and it goes to sec squared x. Now, you'll notice that we actually have a sec squared x here. So when we bring the dx over, we get sec squared x dx. So I can actually replace this whole thing with our du. And I can replace this part with our u, which makes this so much simpler. So when we can use u substitution or integration by substitution, it is so straightforward to integrate. So this, we have something really, really straightforward. We have e to the power of u du. So that means e to the power of u does not change. So that's just going to be e to the power of u. I don't need a plus c or anything like that because I have a definite integral. Now here's somewhere where it can go wrong, and that is by plugging in too soon. Please don't. You have to remember that the limits of integration that were given were for x and not u. So what we need to do is plug back in our u, which is tan x, and now we're going to evaluate between pi over 4 and 0. If you're wondering, like, well, where does the sec squared go? Think of this, because it is the opposite to the chain rule. Like, if we had started with this to begin with, we would have differentiated it, which would have just stayed e tan to the power of tan x, multiplied by the derivative of tan x, which is sec squared. So that sec squared was brought into this when it was differentiated. So when we work backwards, when we integrate, that's where we got rid of it. So this is going to be e tan pi over 4 minus e tan 0. If you've skipped any of the video, I did go through why we have to use radians in our integration and in calculus in general. So it's really important that we remember that they are in Radians, I prefer, if possible, to use page 13. So the tan of pi over 4 is going to be 1. The tan of 0 is going to be 0. So we end up with e to the power of 1 minus e to the power of 0, which is e minus 1. And that is our answer. So integration by substitution is actually a little bit easier than integration by parts. However, you don't have a formula. It is something you need to remember yourself. And what I would say is when we're working through questions, it's one we look for before we look for integration by parts. So before I finish off our last few examples, I just want to kind of touch on something that will be more important when you get to differential equations. But it is important, I suppose, to start thinking about it now, because integration, generally students find it absolutely fine when we're told we are now on a section and you are doing integration by parts and you know it's integration by parts and you can apply it. Or then I say, here we're in a section with integration by substitution, you know that's what we're doing and you can apply it. But when I give you an integration question and I don't tell you which technique to use, that's where students tend to fall down. It's like, how do I identify which technique to use? So we've now met a number of different ways to integrate, and hopefully you are or will become good at doing each type. But in a question, the method for what method for integration should you use? And this is where identification is key. So we really only have 3 ways. You have your basic rules, which is basically look at page 26. You have your integration by parts and you have used substitution. So what I suggest you do is use this checklist. And the checklist is in a very specific order. So the first thing I would do in a question is check, is there a formula on page 26? And if there is a formula, use it. Okay? We have very clearly talked about which kind of versions of these formulas you might be able to work with. So like a version of 1 over x that may be backwards chain rule, cos x tan x. Okay, they're the cos x sin x. They're the ones you might be able to kind of apply a little bit more to it. But generally we're talking just basic formulas on page 26. The next thing to check is it a composite function? So actually, I would check for composite function next. And if yes, use integration by use substitution. So that's integration by substitution. So that's the second thing I would check for. And then the last thing, and it is the last thing, is try integration by parts. So this is the messiest. And there are cases, and we'll see them in a second, where integration by parts will work. And you know, you are going to not just be asked to do these, but do these under time pressure. So I've often looked at questions with students and worked them through, but a question that could be half a page with use substitution could be 4 or 5 pages with integration by parts. So it's not that it's not possible to use integration by parts, it's just time consuming. And if we can use substitution, we try to use that instead. Now, integration by parts, remember, it is about multiplication. So it is about 2 bits multiplied together. So, you know, sometimes we can't get away from it and we just have to use it. But getting to grips with this little checklist and looking at each question and thinking, would I identify that if I were given this in exam? It's so good. So helpful. It will stand to you. Especially keep this checklist beside you as you move into differential equations. So here's example 11. So here's one that I think can be a little bit tricky. And I've put in kind of 2 tricky ones on purpose for the integration by substitution. And I say tricky, I mean tricky to identify that they're use substitution. So from an identification point of view, that can you see this as a composite function? And like majority of students might be like, not really, maybe. So the fact that it's a square root, so the square root is x to a power. So that's like a bracket to a power, but in it is an x squared plus 1. That's why it's a composite function. But it is harder to see. Now here's an example where I've been asked in the past, can you change that to x squared plus 1 to the power minus a half and use integration by parts? Absolutely. Do you want to? No. Okay, integration by parts will work in theory, but you do not want to approach it. It is not the most efficient way to work. You will not have the time to do that in an exam. You need to be able to identify this as integration by substitution. So is there a substitution that you could use? And the answer is yes. We have the square root of x squared plus 1, so we can identify, maybe after a little bit of practice, that this is my inner function. A really kind of nice way to identify the fact that this is integration by substitution and not integration by parts is something I mentioned when we did integration by parts, and that's this in LATE, so in late, in latte, whatever way you want to say it. If I were to say to you, here is integration by parts, we end up with two algebraic pieces, okay? So both the top and the bottom line are algebraic. So remember I said at the end of this slide earlier on, if both parts are the same, so both algebra, for example, then we have a more suitable type of integration to use, and that is integration by substitution. So bear that in mind. I just want to draw your attention to it because it is the kind of thing that actually maybe in an exam you might go, oh my God, I never thought about that deeply enough. So let's go back and actually start working with that. So our inner function here is what's under the line and under the square root. So our u is going to be x squared plus 1. Then we're going to differentiate that. So we get du dx, and that gives us 2x. So we're going to have du equals 2x dx. Now, all I have to kind of take out with my dx is an x. Okay, so I don't want that 2 there. So I'm going to bring my 2 back over the line and have a half du equals x dx. And now I can replace. So I'm going to integrate between root 3 and 0. So we have our definite integral. I'm going to put a half du up here, and that's the square root of u on the bottom. So we manipulate the du dx line, so these lines here, until it's something that we want. So I only want the x dx together. So I'm just going to tidy this up a little bit so it's a little bit kind of easier for us to manage. So that is 1 over 2 is on the bottom and the root u is on the bottom, and then we have du. So in terms of what that is, it's a half. Bring the root u over, that's u to the power of minus a half du. When we integrate that, we add 1 to our power and divide by our power. So the half sits there, it's a coefficient. We add 1 to our power, so that's power of a half. Then we divide by a half. Be careful, sorry, this should be gone. Be careful when you're dividing by a half. Dividing by a half is the same as multiplying by 2. So here we have a half on the top and a half on the bottom effectively. So u to the power of a half, we want to make sure before we do any substitution, remember our u we put in, those limits are for x. So we're going to do back substitution, which means we're going to plug back in. So that is the square root of x squared plus 1. And we're going to evaluate that between root 3 and 0. So that is the square root of root 3 squared plus 1. And then we're going to take away the square root of 0 squared plus 1. That is 3 plus 1, which is 4. So we get 2 minus 1, and our final answer is 1. So here's our last example of the video. We're looking again at integration by substitution. This is probably even tougher to see as a composite function. And the reason it is a composite function is we're actually looking in our log tables. Look at your page 26. And the function we're focusing on is 1 over x. And the version we have here is actually 1 over x plus 2. So this is, we kind of looked at a few of these earlier on. If you just had 1 over, how you're using your log. This one has an x in the top as well. So that's why we're going to use the u substitution, because it'll be a little bit trickier. But effectively, that bottom line, that is our u. Okay, again, a hint why you definitely wouldn't use integration by parts. It's both algebra, so it's really about focusing on what would be sensible as my inner function. So you want to take something quite complicated to simplify the integral. So by taking u, then du dx is just 1. So du equals dx. Now, this then doesn't give us something particularly nice because we end up with x over u du. But we still have an x, which we don't want. So we have to be a little bit clever with that. And we're going to go back to this line here because I can write my x in terms of a u. If I rearrange this line, it becomes u minus 2, meaning this is what my integral becomes. Now, looking at that, you might go, how is that any simpler than what we started with? And the answer is because we only have one thing on the bottom. So we have a u, one term, rather than x plus 2 that's in the original. This is much simpler because we can integrate, and this is something you should be familiar with in maths because we don't have any fancy integration techniques. You would have hopefully learned how to break out your polynomials like this. So rather than writing these as one single fraction, we're going to write them as two different fractions. You can only do that where there's a single term on the bottom. We couldn't do that like here. That is not the same as x over x plus x over 2. That's not how that works at all. Okay, so think about if you were adding these fractions, how common denominator, and then you just bring the top lines together. So we just need to be a little bit clever. Don't automatically assume it's not substitution just because you're struggling to get rid of one of your terms. Really think about how could I be clever here? Where could I write x in terms of my u? So I now have something much simpler. It is 1 minus 2 over u du. And actually, I'm going to rewrite, instead of 2 over u, let's write that as 2u to the power. Actually, no, sorry. We'll leave it as 2 over u because that's as it's in the log tables. So then integrate 1, that goes to u, minus 2 over u. That is like 2 times 1 over u, which is going to be 2 ln u. You can put in those absolute values. That's absolutely perfect. And that's between 6 and 0. Remember, we are not plugging in for u. You're plugging in for x. So let's replace our u with our x, and that's ln. Because of our values, I'm just going to write that as x plus 2 without the absolute value signs because I know we're plugging in a 6 and a 0, which is fine. And then we're going to evaluate that for 6. So 6 plus 2 minus 2 ln 8 minus 0 plus 2 minus 2 ln minus 2 ln 2. And this answer, we want to write it in the form p plus or minus ln q. That plus or minus means it's one or the other. So tidying that up, we get 8 minus 2 ln 8 minus 2 plus 2 ln 2. Let's write that out again so we can see it really clearly. So that is 8 minus 2 ln 8 minus 2 plus 2 ln 2. Now, I have a p, so 6. That part's fine. I have a constant on its own, but then it should be plus or minus a log, which I don't have at the moment. So first thing I need to do is think about my rules of logs and how I can maybe clean these up. So the first issue is the coefficients. So I'm going to get rid of those and write them as powers. So that's going to be ln a to the power of 2, which is 64, plus ln 2 to the power of 2, which is 4. I'm going to use my rules of logs. Subtraction means division. So that's going to be plus ln 4 divided by 64. And that's going to give me 6 plus ln 1 over 16. Now, slight issue here in the sense they told me p and q both had to be natural numbers. So what I'm going to do with my natural log here is I'm going to flip it, and that's going to make it a minus. So I get 6 minus ln 16. So what I could have done here is I could have put the 64 over the 4 and made it negative. I'm just going to bring this part over here and explain it a little bit more for anyone who is not so comfortable with the logs. So all I've done here is I've said, well, that is the same as ln 16 to the power of minus 1. And then I put the minus 1 in front, which is simply minus ln 16. It's a nice little trick to know and to have.